Riemann integral. Okay, let me just review the just to make sure what has or hasn't been discussed yet. Okay, so integration. That is anti-differentiation issues that we discussed. Okay, so magnitude of functions, once again differentiation, more applications. Where are the integrals? That's still the same. Okay, so here we started with the Riemann sum. That is the computation that it takes you all the way through. We did it only once. So it's because it's so hard from scratch, starting from the function, the origin, Riemann sums, a limit. Inside of the limit, we had to do that algebra from we also discussed yesterday, and then finally the answer. Okay, 2/3. So the area under the parabola, this parabola from 0 to 1, is 2/3. Okay, then we discussed the remember integrability that follows from continuity. Every continuous function is integrable, but some functions, such as step functions, are also integrable. Okay, then we turn to integrals, definite integrals, and specifically some of the properties. They all follow from properties of Riemann sums. Okay, so that is illustrated right here. So since we are turning back to Riemann sums and that transition to limits, one more time to be discussed. So that's what happens is remember that on one hand, either Riemann sum or the integral, they both about the area under the graph. Okay, except the Riemann sum is simple because it's made of bars. Those bars, by the way, don't assume that they could stick out from under the graph, right? As you know. But with that, so it's just an approximation, but because it's just a sum, rather than the limit of the sum, these things are very visual. Okay, so you just if you have two functions and then you stack one function on the top of the other, what do you have? You have the sum of the two functions. Okay, and then what happens to the Riemann sums? They are being added as well. Okay, so that produces a property of Riemann sums, which in turn produces the property of Riemann integral. So that's what we are looking at right now. So this line is the properties of Riemann sums. They are just sums. Okay, so with the sigmas, it's just a notation that makes things more manageable. But this one, the last one we're really interested in, the last line, is how we can break summation inside of the integral. If you read from right to left, that summation on the right can be broken into two integrals, just like sum rule for derivatives. And then similar, the constant multiple rule, once again, we're stretching a function. What happens to those bars? They also stretched. Okay, so that, which means that the Riemann sum works in the same manner. You factor that component, or that factor, you factor out of the Riemann sum, which means that under the limit, the same thing happens to Riemann integrals. Okay, so then the area, that curved area, not what they made of bars, but actual curved area, have this property. So you stretch this curved area. So imagine you have a curved area and then you stretch it vertically, say by a factor of 2. What happens? Well, the region stretched produces stretched area. Not stretched area, but rather multiple of the area. So the area is a number and the region is the region. Okay, so if you shrink, same story happens. So you cut it in half. It's really just like a piece of rubber. Imagine that this one is drawn on a piece of rubber, and then you stretch it in the vertical direction. Then every little piece of the rubber becomes doubles, and then the area doubles too. Okay, so these are two very straightforward property. And the next one is hold on, we didn't discuss this one. Did we discuss the additivity? I don't think we discussed the additivity. Okay, so this is again constant multiple rule in the sum rule. Okay, but so then the discussion was of the fundamental theorem of calculus. So Riemann integral, midpoints. We compute the Riemann sum one more time, and what we're after right now is there is one more very simple property. Also comes very naturally, and that is in fact, I should have put it beforehand. So how about I put it here at the bottom? Okay, so additivity property of Riemann sum and integrals. Okay, so it is very simple. Simply cutting what we are being added is not the functions which is in the sum rule, but rather the domains of integration. So domains are added. Domains say A, C, and then there is a domain C, B. Okay, so it's you could have the same function, right? Y equal f of x, but then the domain is broken, as you can see, into pieces, and like this, and therefore the areas are also broken into pieces. So one area, and then the other area. It's a very intuitive thing to understand, but especially when you talk about the Riemann sums, because it's once again just a bunch of bars, and then literally if you have a bunch of bars like this, okay, and then you have more of these. So you add these, the green one, then pink ones, and then it doesn't really matter how you're going to add them. They add up to the same to the same number. Okay, so these are Riemann sums, and these are Riemann integrals. Okay, so the way we put it is this. So the property is the integral from A to C f dx plus integral from C to B f dx is equal to integral from A to B f dx. Okay, so that is the additivity property. So the point is certainly is to make sure that we throw around such a idea or as area, it makes sense, sort of what our intuitive understanding of the area is still with us. Remember that the area is, we pretty well understand mathematically what the area of a rectangle is. Beyond that, we have to rely on our intuition. And one thing is that you have to kind of two quantities, two objects put together. Unless they overlap in some significant way, they should the sum of the quantity here, quantity there, put them together. What happens? The quantity is also being added. As you can see, the quantity I'm talking about are the areas, and the only thing to worry about is the overlap. The domains do overlap, but only by 1 point. So which is why it does matter that it does not affect the area. So 1 point does not change the length of the two domains, and the area as well does not change. So altogether, that it is intuitive understanding of quantities, of areas, volumes, mass, anything you can think of. It is right here. Okay, because remember that it is just an interpretation, that the area is an interpretation of the integral, but ultimately it is math. So any kind of function could represent any quantity. So you can imagine, so just depends of the quantity of one quantity on another quantity, y on x, and then we want to know ultimately the total amount of that of y's present, and then that's the integral. Okay, and then it still works out. So we use this area idea as a metaphor for things that are more general. any kind of quantities. So like I said, it could be mass, for example. Could be imagine that one good application that's worth discussing later is the density. So you have a rod. Which is along the x-axis, okay, and then you have density that changes continuously throughout the rod, which could happen, say, if you have it's made from an alloy or two alloys. You have two alloys, and then you connect them together, and they sort of start to melt one into the other, but not completely. So the end result might be some kind of increasing density. Okay, so continuously changing density rather than incrementally. And then you might ask yourself still, what is the mass? What is the mass? And the answer is, you integrate the density. Okay, so every piece of think Riemann sums. Think Riemann sums. So if we have this rod, okay, so how do we understand the meaning of the density as well as the mass? We cut it into small pieces, okay, and then take every piece and sort of measure its density. So the function f is defined here, but what is its meaning? Its meaning is the density. And then what is that? The density is a linear density, so it depends only on the width on the horizontal location. So you multiply f of x times delta x. So each of these is delta x, and what does it give you? It gives you the mass of every little thing, every little piece together. And then when you piece them together, you have the mass of the whole thing. However, it remains an approximation. If the density truly is changing continuously, then the only way to actually understand what the mass is through the limit and through the integral. Okay, so then the function becomes like this, and then the total mass is the integral from a to b f dx. Okay, so the exact same thing. And then the additivity property tells us that so if we cut our rod in half, then we just can treat these two things separately and then add them together, which is what you expect from mass. Okay, so and then density certainly could be any quantity. A lot of quantities can be discussed in terms of their density. Quantity. So mass would be this distribution of weight. The density is distribution of weight. But you can talk about concentration of a particular, say if you talk about you talk about the still a rod, but you're not talking about mass. You're talking about, say, the amount of maybe it's say it's made of alloy of gold and silver. So then you might ask yourself, what is the density of gold, period, and ignore the silver altogether, and then that amount of gold will be how it is distributed throughout the rod. Or it could be gas in a tube, and once again it changes continuously, and once again there's a density of gas. It could be density of population, anything you can think of. So it's just a function of one variable that actually capture a lot of things that are happening. And the integral tells you once again the total amount of that material, the density of which material or medium, whatever it is, and the total amount is then revealed by the Riemann integral of that function. Okay, so the property are all good. There's I guess there's one more property. It's called, let's call it estimate. It is based on a function that is between maximum and minimum function. So suppose m is the minimum f of x on integral ab, and m capital is maximum f of x on the integral ab. Okay, then what can we say about the integral from a to b f dx? And the answer is there we could estimate the value of the integral. So in other words, if you think, so can you tell what the answer is? What I should put here and there? Well, since we're talking about density, think about density. So suppose F is the density, and then M, lowercase, is the minimum density. Okay, so the integral itself is the mass, okay, of the exact mass of the whole thing. But if you know only the minimum density, then you can estimate the total mass. What's the total mass? What is the smallest possible total mass? The minimum, that's the density multiplied by the length, right? So because it's linear density, so M is the minimum linear density. So then to get the whole thing, you multiply by the length of the rod. Okay, so another interpretation is, so we have been talking about density, but let's not forget they actually just as good or even better interpretation or a way to understand the functions of one variable. It is the velocity. So just take a totally different look at the situation. Instead of f the density, what if f is the velocity? Then the integral is the displacement. So if you know the minimum velocity that you have had, then you estimate your displacement by being say you suppose you're moving at least 50 miles an hour. It means that in an hour you're gonna cover 50 miles. In 2 hours you'll cover 100 miles, the minimum, right? And then on the other end, you looked at your speedometer. You know that your speed never was above 70 miles. But you know in an hour you're not gonna pass 70 miles, and the 2 hours not 140 miles. So on the other end, the maximum will be similar. Okay. So once again, f is integrable. So that brings us to a very nice concept of this theorem, a very nice concept of the average value. So as you can see, what if I go ahead and divide this double inequality by b minus a, so it will be 1 b minus a from a to b f dx. It will be between m and m capital, right? So then what is the meaning of this number in the middle? And the answer is it's not really, it is a concept that is introduced based on the concept of integral. It is called the average value of f, of y equal f of x. Okay, we know what the average means when you have a few numbers. What do? You just add them together, divide by the number, or by how many you've got, right? So 2 numbers divided by 2, 3 numbers divided by 3. But what if you don't have a finitely many number, but you have infinitely many numbers, and it changes continuously? So that graph of f is what might be representing those quantities. So for example, you could ask yourself, what is the suppose think of this as like a sandbox, say. So it's sandbox filled with sand, and the top is curved, okay? And then you might still ask yourself, what's the average height, okay? So what do? It's either if you don't want to do computations, what you do is you just level it. So you still have the same sandbox and the same amount of sand, except you level the top. So it will look like this. So certainly it is justifiable that since you didn't lose anything, then this is the average value of the function. Okay, so that is what calculus gives us. A lot of things that conceptually were simple somewhat. When you have just a few numbers, it's either adding them, multiplying all the algebra that we have done. It is about it's also areas, volumes, and so on that they know. And this is another one. Well, averaging things is a fairly straightforward idea, but only when it is only you only have a finite number of numbers, a finite number of numbers, and but it's also we can now handle infinitely many numbers in this fashion. So anything. Say, suppose a moon goes around the Earth, and you might ask yourself, for example, what is the average distance from the moon to the earth, or the average distance from this earth to the sun, and so on. Once again, there are infinitely many locations. There's a formula for either one of the trajectory. So in other words, you do have a function just like that over there, and you can just plug it into this formula. If you can carry out this integration, which is possible, then you will know the average value. Okay, so that's very convenient and used a lot. It is in a way also very applicable to things such as probability theory, which deals with densities of random variables. Okay, and then when those variables are discrete. So have you seen any probability anywhere elsewhere? Well, so like if you toss two coins, what's the probability of getting three heads, or I'm sorry, two heads in a row? 1/4, right. So roughly speaking, you are averaging. You have to look at all the possible outcomes, okay, which is 4 possible outcomes, and only one of them is two heads in a row, and that's how you get 1/4. Okay, but what if the value change continuously rather than incrementally? So you have infinitely many possible outcomes. For example, you are shooting at a target, okay, and then certainly there are no particular locations where you're hitting, so that you can put them neatly in a basket, but rather they can be distributed uniformly. Any point is a possibility. So how do you, for example, evaluate from the data that you've got the probability of hitting the bullseye? Well, that's how roughly you integrate over all the possible the function over the bullseye, and then take it as proportion to the whole thing. Okay, so and that amounts to the average value. Well, maybe targets. Well. Yeah, so I just let me take another take at it. So what it has to do with probability? So what is the expected distance from us to the sun at any given moment? Well, that's how you just take it is the expected value means the expected distance is simply the average distance. And so it is at random time, you pick it, and the most likely possibility, the most likely then what you see most likely is that average distance, because everything is distributed more or less around it. And then this is how you compute it. So it's just the same pretty much stuff, except can be interpreted in terms of probabilities. So anyway, you cannot really do any probability beyond the most elementary without calculus. Okay, so if in case you engage in that anytime in the future. With these 3 properties, we are in a pretty good place. We could do a lot of things with integrals, but ultimately we have to learn how to integrate them, how to actually carry out these computations with specific function. So we'll get to that, but first we have to, okay, sigma notation. Okay, well, let me once again state this. I think we have stated it before, the most basic theorem. So constant function fx dx, so not fx dx, 1 dx, okay, so is b minus a. So 1 is a constant function, so it certainly is integrable, and that when you evaluate that function, that integral with this function, you end up with what? The length of the integral. So that plus some of the algebraic property will give us the initial those 2 algebraic properties that we have. let's take a linear function. So a linear function from a to b. And how about we have mx plus b here? Okay, so I could do the Riemann sums, or we could just use a common sense and deal with the algebra of actual areas. So this is my y equal mx plus b. That is my function, and that I guess I'll have to replace b with something else, otherwise I have too many b's. Okay, so I'll say s. Okay, so s for the y-intercept. Okay, so and this over here is a, this is b, and this integral is the area. So what is it? What's the area of this shape? What's the name of the shape? It's trapezoid. So what's the area of the trapezoid? Anybody remembers? Height times what? Yeah, base 1 plus base 2. That's right. Okay, so certainly we have to tilt it, because then now this is the height, and the other one are the two bases. So this is, say, base maybe 2, and this is base 1. Okay. Okay, so well, we just read this off the picture. 1/2. The height is b minus a. Okay, what is base 1? Yeah, okay, so but we have a specific formula for the function, so we can tell what it is. So what's base 1?
MA plus S?
What?
Would that be MA plus S?
Yes, MA plus S, that's right. And the other one?
MB plus S?
MB plus S. Okay.
It took me a second. I wasn't sure if there was a specific formula we went over before, if we just were supposed to plug it in there.
Yeah. So yeah, we picked a specific formula. So every time the function is chosen specifically, the output of this integration will be nothing but the specific number. So we did it with the constant function. But incidentally, if I put any c here, then it will be simply an extra coefficient. So if you by the constant multiple. So I just want to have a picture just as well. We have picture here. We can have a picture there too. So if this is y equal to c, that's our function. Then the area we're talking about is this. So you multiply b minus a, the base, times the height, c. Okay, that's all there is. There's a very simple, as long as the function is simple, there is a simple geometry behind it. Okay, so I could suppose I can simplify this. So what is it? B minus a. S, and here I will have m a plus b m. How about this? A plus b over 2. Okay, I'm not sure why this is supposed to look better, but it looks okay, I think. So it will be the average between the endpoints. Yeah. Okay. So okay. So do you see what this is? I'll note this is the same formula, mx plus s, except I substituted in it a plus b over 2. What's the meaning a plus b over 2?
Would that be X?
It will be on the x-axis, a particular point on the x-axis. What is it?
The average of the two X's.
The average of a and b, so or midpoint. So this one is a plus b over 2. So then it is being substituted in my formula, so that what I have here in parentheses is in fact this. Okay, so I forgot, what's the name of this line? Midline, well anyway, it's the average of the, it is still the average of the two bases, except it is a middle line, and it is the average, and it is half of the sum. So anyway, it doesn't matter. We have a specific number. We can verify it. It works for any. The advantage of what we pursued this pretty carefully integrals, and we want to make sure that, for example, functions that don't have to be positive, doesn't have to look like this in order to be subject to integration. So which means that what we have done, it works just as well if my graph looks like this. It doesn't matter how it looks, like this. So it could be still. It could be, say, this is A and this is B. The part of it might lie below the x-axis, part above. The slope might be negative or positive. So I'm talking about this area, which is not a trapezoid anymore, right? But the formula will still apply. Okay, as we'll see later. So remember that this will be negative, and this will be positive over here. So this part is positive and negative. So altogether is negative, and it turns out that there is such a thing as the trapezoid with a negative area, as long as the if it is located appropriately in a particular way over relative to the x-axis. And so if a large part of that trapezoid lies below the x-axis, then we'll have the area also negative. Okay, well, which is, frankly, it doesn't even look like a trapezoid. I mean, it's two triangles, but the formula still works. Okay. One more thing it is just worth mentioning is the non-integrable functions. Once again, one is, say, well, this one is easy. Say it is equal to 1 over x if x not equal to 0, and it is 0 if x is equal to 0. So the graph is looks like this. Okay, so if we're talking about the integral from 0 to 1, so the function is defined on this interval. The trouble is, so let me, I got to be specific here. So this is my graph. So it follows the function 1 over x, except that 0 is equal to 0. Okay, so it certainly makes the function discontinuous, but more importantly is the question becomes, what is the meaning of the area under this graph? You can easily plot it. This is what it is. That's supposed to be the area, but you realize that what we know about asymptotes, that this part will continue on forever, because that branch will never touch the y-axis. So, in other words, it is an infinite region. Okay, so in that direction, it is infinite region, and we just do not, well, it just happens to be infinite area. But it doesn't have to be the case. So that in Calculus 2, you'll see examples of infinite areas with infinite regions with finite areas. So some of the areas are thinning so quickly that they add up to a number rather than infinity. Okay, so it's also possible. But in this particular case, the function is not integrable. Why? Because if you try to build those Riemann sums, they will be even though they are getting those rectangles getting thinner and thinner, they will be thinning slower than they will be growing in height. Okay, so it's like this. So if I take one of the rectangles here and then start to refine my partition, then it will be getting thinner and higher, like this. Thinner and higher, and then more. Okay, so that's what's happening. So this is refining the partition. Okay, and that's the thing about that. All depends on the nature of the function. In this particular case, while the width of the rectangle is going 0 at a certain rate, the height is growing at a rate that is higher. And when you multiply them together, the whole thing goes to infinity. But it doesn't have to be. Okay, so it depends on the how fast the function is growing. This one is growing pretty fast. Okay, so that's still to be examined later on in calculus 2. This point we'll just point out that there are really nasty functions. This is another one that's way nastier than that. It is the function that is well, this is the function 1 if x is rational and 0 if x is irrational. Okay, so this one is really hard to plot. It's not only discontinuous, it's really just if you need another example of discontinuity, that's what you've got. This function is not only discontinuous, it is discontinuous at every single point. Okay, why? Because the rational and irrational numbers are intermixed. Okay, so if you take two rational numbers, there will be always an irrational number between them, and vice versa. So which means that that gap of values 0 and 1 will never be breached, and there is always a sequence. This is how we see the discontinuity is. Say if say S is irrational, then there is a sequence Xn rational that converges to it. In fact, we discussed at some point what that was. How do we find a sequence to converging of rational numbers converging to the irrational number? Just the decimal representation. So the decimal representation of an irrational number has infinitely many entries, and you just make it longer and longer and longer, but finite. So if you cut off less and less, or keep it more and more from the infinite string of numbers, it will create a sequence, and each of them will be a rational number. Okay, so decimal, the truncated decimal representations of the irrational number gives you a sequence of rational numbers. And then you realize what the trouble is, that f of xn will be equal to 1, while f of s is equal to 0. So you see that is a contradiction to our definition of continuity, because 1 does not converge to 0. So a sequence of numbers converging to s, okay, but they produce under function f something that with no convergence. Okay, so no convergence, so which proves simply that f is discontinuous, which is not a big deal hypothetically, because discontinuity does not disqualify the function from being possibly integrable. But this one is integrable. This is really bad behavior, and also there's certainly some argument to be provided that to see why it is not integrable. One way, well, let me first try to plot how do I plot this function. Think about it. So this is y equal 1, and this is y equals 0. I have infinitely many points on this one, and I have infinitely many points on this line. Okay, with nothing in between, and the function is infinitely frequently oscillates between these 2 points. On and on, you can't even follow. There's no kind of a process that you can describe that what's happening, how you alternate between the two. So you can try to build a Riemann sum. If you build a Riemann sums, you can build a sequence of Riemann sums that each of them is equal to 0. Okay, so you just choose the rational sample points. So rational sample points of your partition gives you Riemann sum equal to 0. I'm sorry, to 1 over integral 0, 1, and irrational sample points will give you Riemann sum equal to 0. Okay, so which means that once again there is no convergence. There is no convergence. So, and that is the definition of integrability, is that the partitions being refined is supposed to produce the same limit, and these two do not. Okay, so that is the definition that I was supposed to put here somewhere. Well, I did. So sample partition, total area, and I didn't indicate the limit, the last step. So so we have to say that that's what the limit delta xk goes to 0. So that's what produces the Riemann integral from Riemann sum, is when the widths of those bars get thinner and thinner. But it's not only that what's supposed to happen. What if you do it in a different way and it produces different results? That is not integrability once again. Okay, so let's see. What else do we need? So we already stated the properties at that point. So we have properties almost identical, or properties of Riemann sums versus Riemann integrals. So that is the sum rule, one and the other; constant multiple rule, one and the other. They're almost identical. Additivity rule the same, and the estimate rule. Okay, the estimate rule. These are the main ones. So so that's always, if you in any doubt, you can go back to Riemann sums and confirm that those properties, because after all, the what we have seen with especially with Excel, I suppose especially what to be useful in that respect is okay, that is not the right one. Not the right one. Well, this is I guess as good as illustration as it is. So even though you start with the Riemann sum made of big chunks, and you can see that it's a sum, you can see the bars, but ultimately you end up with something like one of these. Okay, so they start to look like a curve, and as you proceed doing it, this is only had like 20 n equal to 20 integrals. If you have 100, you have 100 bars, or a curve forms more and more like a continuous curve. So you cannot really tell them apart. So is this integral, or is it this Riemann sum? They are virtually indistinguishable. That's the good thing. That's what we did in class when we computed the area, or approximated the area of a circle. So this was done with no more than just 20 points, and you already can see that there's a circle there. And so Riemann sums are really very useful tool for understanding integrals, because they behave in a virtually identical way. So and then what we later on discussed, just a couple of days ago, was the fundamental theorem of calculus. So let me, and that was done with the Riemann sums to begin with. So so the way I described it was here somewhere. Yeah, so apply the Riemann sums to the function of difference quotients, and you have the original function. Well, so if we do the same with after limits, not before, then we're talking about the interrelation between the derivative and the Riemann integral. Okay, and they have the same property. So that deserve discussion from scratch. So let me start this way. So the area function. So remember, the integral is a number when the limits are fixed. So f dx is a number. So once a, b, and f are specified, it gives you a number. Okay, but we could make a function from this. We start with a function f. We have the whole graph here, so we certainly can do that. So even that number, it represents the area. Okay, but what if we start varying the upper limit like this? Okay, so how about f of t? Okay, so the same function, the same setup with a and b, but the upper limit is variable, just as we did with Riemann sums. Okay, so this is a, And then well, let's say that's B. I have a t here somewhere. Not one t, but many t's. For each value between a and b, I could pick a t, and I could define an interval. It is then this interval over here is this area. Not the whole area, but piece of the area. And as I progress, t progresses from a to b, the area grows, or maybe declining, I don't know, and it gives me, it creates a function. So that's called the area function. So all we have to show then, we'll do it next time, that this f prime of t, the derivative of this function is equal to what?
The average slope.
No, maybe. Well, the answer is f of t. Once again, if you forget about integral and derivatives here, we're talking about the Riemann sum and difference quotient. So the first function is the Riemann sum. The second function is difference quotient. We know from discussion from 2 days ago is that if you combine these two operations, you come back to the original function. Okay, and that's exactly the same thing, except we're dealing with the concepts that are more complex, but they're the same concepts. The derivative is just the limit of a difference quotient, and the Riemann integral is the limit of the Riemann sum. Okay, so that is, we already saw something like that, and we'll just have to pay more attention to this and spend some time talking about it. Okay, so homework will be assigned later today. Okay.